So what our project is we are looking at how BYU is studying the possibility of predicting stellar parameters using photometric filters. They believe they may have a spectral index that could predict stellar parameters such as the temperature, gravity, turbulence, and metallicity at the surface of a star. Our goal was to test BYU's spectral index on a set of stellar spectra of stars that are, in my case, in M13 collected by Sloan Digital Sky Survey. One thing of note is that we found that the spectral index is best for predicting the temperature at the surface of a star rather than the other parameters. I'd like to begin by addressing what Sloan Digital Sky Survey is, which is where we got our star spectra. As Wikipedia says, Sloan Digital Sky Survey, or SDSS, is a major multispectral imaging and spectroscopic redshift survey. In short, it is a project with a goal of mapping the universe. In order to gather star spectra, SDSS aims an aluminum plate that's 2.5 meters wide into the sky. The plate has a hole in it specifically positioned for every astronomical object that they wish to observe. Each hole is marked to correspond with an optical fiber that will be connected to it, which will gather data on its targeted star and stream it to a spectrograph which separates the light by its wavelengths and records the data. Because the holes are positioned on the plate according to the position of the objects they are observing in the sky, a unique plate needs to be used for every field in which the spectra are gathered. The original spectrograph attached to the telescope was capable of recording 640 spectra simultaneously, while the updated spectrograph for SDSS-3 can record 1,000 spectra at once. That means 1,000 holes in the plate and 1,000 fiber optic cords attached to each individual hole in the plate. The telescope tracks the field it is observing in the sky, keeping the objects focused on their corresponding fiber tips. Over the course of each night, between 6 and 9 plates are typically used for recording spectra. Every night, the telescope produces about 200 gigabytes of data. So that, if you imagine, is 6,000 to 9,000 holes that are drilled every day in aluminum plates. I think I know where one guy who talked earlier where his aluminum went. As previously stated, our goal was to apply BYU's spectra to the BYU's spectral index to the spectra of stars and see if it can predict certain stellar parameters of those stars. To do this, we chose each an individual cluster. Something that does for us is it isolates the metallicity, because stars in a cluster have a similar origin. They have a parameter, which is the metallicity or the makeup of the star, that is kind of similar in all the stars in the same cluster. This allowed us to isolate one of the variables that was in our data, and if we wanted to take into account the metallicity of that star, or a wider variety of metallicity of stars, then we could use all the data combined that all of our colleagues had taken. The cluster that I chose to use is Messier 13. Stars in the cluster are relatively similar. Let's see. This cluster has a density of stars that is more than 100 times the density of stars around the space of our sun. That means that in some cases they will actually even collide and create very hot, very large stars that we call blue stragglers. In applying BYU's alpha and beta indices, which my colleagues went into how that is done, these are the graphs that I got. The y of these graphs, the y variable, is the surface temperature at the temperature at the surface of the star, and of course the index is the measured value from the filters that we get. An important thing to know about these graphs is the R value. The R value is effectively how clean they are. And as you can see, these are very messy graphs. You can't just kind of splatter. You can't exactly tell if there's that much of a correlation. Something that we noticed as we worked on this project, as was previously stated by my colleagues, is that the narrow filter seems to be more effective, and as you can see, that's a lot higher of an R value on the narrow filters. This is the beta alpha, and this is the beta line. The narrow filter was a lot more accurate in determining the surface temperature of the star. This got me thinking, however. BYU claims that they found more accurate values, that what they wanted to do is get the full index of the star with using both filters. And since they've used it for a while, I've wondered if there was some situation that I can find where the wide filter being used in conjunction with the narrow filter was more accurate. What I came to was looking at the smoothness of the spectra we used. These are some examples. These are normalized graphs. One of my colleagues will get into that in their later presentation, how we normalize the graphs. But as you can see, some of the graphs were very smooth, some were kind of all right, and then some were totally a mess. I had a thought that maybe for the smoother graphs, the full index rather than just the narrow filter might be more accurate. As I got into looking at what the narrow graphs were, I found that, or the smooth graphs were, I found that the hotter stars, the top star here is a cooler star, the bottom is a hotter star. I found that the hotter stars were typically smoother. This kind of makes sense because hot stars just give a whole lot of raw light out. That's a lot of signal, which means a lot of signal to noise typically. And I didn't want to just focus on my hotter stars. So I went to, instead of just looking at the visual smoothness of the graphs, I decided instead to use the sound noise values that were given by Sloan Digital Sky Survey. Something that I found is that for the hot stars, sometimes they were smoother, but they would have a lower signal to noise value than the cooler stars that didn't look as visually smooth. We want the high signal to noise, and so that was good because even though some of these messier looking graphs appeared in them, we got cooler stars in what we measured. These are the graphs that I got after. Now, if you remember, my goal was to see if this is the full index, so it's applying the measurements using the narrow and the wide filter. If you remember, what I was wanting to find is if using the narrow filter in a situation where using the narrow filter in conjunction with the wide filter would be more accurate than just using the narrow filter. And unfortunately, I came to find that even with these calculations, the narrow filters, as you can see, the R value is better and it's a lot tighter of a graph. Doesn't have all this splatter of different stars, same temperature stars across different indexes. So the narrow graphs I found were better representations still. In my spectra, I noticed that taking just the high signal to noise spectra, I had isolated kind of just the really cool stars and the really hot stars, so I decided to use all the spectrographic data that my colleagues had taken, and this is all of the stars that have higher than 58 signal to noise value of my colleagues. Something that kind of came up as interesting to me, I had a thought suddenly as I was going through this, so I kind of didn't get something that showed a situation we would want to use the wide filter in conjunction with the thin narrow filter. But what I thought of later was, at what point do we not want to use our at what point is the signal to noise value too low that we wouldn't really want to use spectrographs or this spectrographic filtering? And what I found is the lower the signal to noise, as you can see, the R value falls. But I did notice that the H beta line seems to be more accurate with lower signal to noise values. This is just a graph of what I had taken along with, or this is my data along with my colleagues' data. And again, these graphs in particular are the graphs with lower than 20 signal to noise value. It's got a pretty bad R values. Again, the H beta line is more accurate. So what I came to as my conclusion, and some of the things that I would like to get to possibly in the future, is I was unable to find a scenario where I feel confident that we would want to include the wide filter in our measurements of the star parameters. My colleagues and I observed that the H alpha index generally seems more reliable than the H beta index. My colleague Benjamin Jantz pointed out that the H beta index seems more accurate at higher temperatures. I noticed that the H beta index may also be more reliable for lower signal to noise spectra as well. I want to note that star spectra are difficult to image, as you may have saw with me talking about Sloan Digital Sky Survey. It takes a lot of work. And the resolution of the star spectra we had was medium resolution spectra. In the future, it would be interesting, I think, to look at higher resolution spectra and see if we can see something within higher resolution spectra that may indicate that there's a situation where the wide filter we may want to use the wide filter in conjunction with the narrow filter. And then I'd like to acknowledge for this project Sloan Digital Sky Survey, where we got our information, my classmates, BYU, as well as my teacher, who is my co-author to this research project. He wrote a lot of code for us, and I am thankful for that. That's a good question. I really don't know that. I didn't really look too much into that. I just saw that there is higher resolution data available. From my understanding, what the process Sloan uses doesn't gather higher resolution data, though I think, I know that you can find it in places. So it wouldn't be from the SDSS. So the filter is we didn't use filters, we kind of simulated the data using star spectra, but as my understanding, BYU simulates the data on star spectra as well. They have glass filters, and what they do is they take the light, to get an index or a measurement, they have two different lenses. One is a wider filter and one is a thinner filter that effectively separates the light of where the H alpha or the H beta lines are. And the way that we take our measurements for the BYU index, they take the light that is in the wide filter and the light that's in the narrow filter, and they subtract the light that is detected in the narrow filter from that of the wide filter. So they actually have glass filters that they can put over top of a microscope to gather this data. Yeah, so the R values of our narrow filters were just better kind of because it correlated more. The linear correlation was better for the narrow filters. Something that was kind of interesting that I can bring up here, I feel like there's some kind of correlation with why, I think there's some kind of thing that the wide filter does indicate, because the wide filter brings these hotter stars out here in kind of the middle index area. And that might be another variable that comes into, such as the metallicity or something, some variable, maybe log G, like the surface gravity of the stars, how massive the stars are, might also be why our R values aren't as good for the wide filter being used in conjunction with the narrow filter, but I couldn't see any correlation myself of why that happens. But it does certainly look like, in this case, for example, that something is happening with the wide filter that kind of likes to put the stars in a certain area. Okay.